the heck does quantum mean?
I think quantum is just kind of like a very specific unit of measurement in some way, shape, or form.
Quantum means like time, space, continuum, maybe like something with like something else. I don't know, maybe Mark Harmon, like the 80s show, Quantum Leap, where you can like time travel. It's for time travelers.
What do you think quantum means?
Even or odd?
Quantum is something to do with physics.
Quantum? Big. Something big.
So you want to know what quantum means? Like quantum leap on the show? I think it means like a big jump, like a big progression on something. Like quantum mechanics, quantum leap. It's just like going from 0 to 1,000,000 quickly.
I have no idea, but I think maybe something to do with like time and space. I don't know, I have no clue.
A quantum is a small rodent native to the Australian desert lands inland that subsists primarily on insects and other dead animals that it finds. It's a scavenger. That's a quantum.
What is quantum?
Nothing.
The word quantum itself refers to a discrete quantity, individual, separate, distinct values. You can think of the volume knob on a radio. Rather than it being infinitely variable as you adjust the control, imagine that it only clicked into fixed, discrete presets. Those fixed, separated numbers are quanta.
In physics, it commonly often means a minimal amount of some quantity that we can measure. This really came into play when in 1905, Albert Einstein was trying to describe the photoelectric effect that was described by Philip Leonard in 1902, actually used the word specifically for radiation. And he used specifically the word Lichtquanta, meaning quanta of light.
So an individual photon, a short burst of light, carries the minimum quanta of energy for any specific color of light. You can draw a comparison between the notion of electric current, which we know comprises a stream of individual electrons, or matter itself, which in its smallest, most indivisible pieces are atoms, or I should be saying quarks and leptons.
But at the same time, you have people like de Broglie in 1922 and Erwin Schrödinger basically saying everything is potentially wave-like. And here's where people often find some reason to be upset with physics, because the question is, you know, is it a wave or is it a particle? And the answer here is that the experimentalist, when they do a measurement, actually imposes upon the system whether it's going to be a particle or it's going to be a wave. In other words, the person doing the experiment, the observer, if you will, matters, because they're going to enforce the system into one aspect or the other.
Trying to figure out where electrons are, in a sense, we got to reach out and touch them, and we will change their momentum. We will change their position so that taking subatomic measurements is interacting with the stuff you're trying to measure.
And the consequences of this are that you cannot separate the person doing the measurement from the experiment itself. This makes some people uncomfortable, not me. I'm happy with it. But basically, if I want to do a measurement, I can do that measurement, but I can't come back to the same system.
What quantum mechanics allows us to calculate is a distribution of probabilities. It can answer questions like, how probable is it that after a given amount of time, the particle will be found here or there, or with this energy or that energy? It's worthwhile contrasting that to the classical understanding of the area of mechanics. Mechanics simply means how do objects move. Newton's laws tell us that given the current position and momentum of any particle and the forces that act on it, we can determine how it'll move. We can calculate a trajectory for us. We can predict where it'll be and how it'll be moving at any future point in time. And so, billiard balls, ping pong balls, footballs, ballistic missiles, rockets, flying drones, crashing cars, all those things are governed by Newton's laws. But as we approach smaller scales, the atomic level, and ask questions about how do electrons move within atoms, then surprising new principles come into play.
On atoms and everything made out of atoms is only there, does only exist, is only stable because of the fundamental laws of quantum mechanics. Because, you can look at an atom and you can figure out that electrons are somehow creating a shell surrounding a positive nucleus. And if you would apply the laws of classical physics, so prior to quantum mechanics, we had only classical physics, then you would realize, well, you have charges that move in a circle or in an orbit. And classical mechanics would say then if that happens, the charge has to radiate off energy. And where is that energy supposed to come from? That can only go so long, and then the charge would fall into the positive core and matter wouldn't be stable. So it requires quantum mechanics to have matter in first place. Without that, we couldn't have stable matter.
Quantum tells us that energy levels are quantized. If you think about what that means, that would be like saying I can drive my car at this speed, or I could drive it at a higher speed, but I can't drive it at any in-between speeds. You'd have to somehow make the leap from the first setting that you click into to the second. That's the quantum leap. And ordinarily, those quantum leaps are incredibly tiny because we're talking about the energy levels of excited states of the electrons inside an atom. Quantum effects are frequently cited, let's say, by science fiction writers as an explanation for things like teleportation or being able to pass through barriers. The X-Men mutant Kitty Pryde, also known as Shadowcat, is able to make herself intangible. And as such, she's able to, what they used to describe as phase through solid barriers. She could walk through walls. Later, following some astute suggestions by fans, they started describing it as quantum tunneling. So they're using a term, quantum tunneling, that describes behavior at the subatomic level to describe something that can be drawn as completely visible in the macroscopic world.
In order to understand quantum mechanics, you first have to understand that physics is not what everybody always thinks it is. It's determined by what you measure in the universe, by experiment or observation, and ultimately physics just is what physics is. It attempts to explain the nature of the universe, but it doesn't mean that physics is necessarily seamless or without internal contradictions.
And everyone would rightfully say that quantum mechanics is the most fundamental underlying theory of matter and everything we describe in physics.
All of physics deals with time and space. And quantum mechanics certainly talks about space, but at this very, very, very tiny scale.
I think quantum is referring to very, very, very small measurements of time, or I don't know, anything like that. Very, very small, minuscule measurements.
A quantum is a type of physics related to very small particles, I think.
Now that's nano.